All right, at the end of section 4.3, we were solving some equations, and 4.4 really just continues that solving equations process. So we're going to see a variety of different types of equations and talk about when they have certain forms, what we have to do in order to solve them. So we've already kind of started that process back in 4.3, we're just continuing it now. So oftentimes, changing things with a scorpion tail is helpful. Sometimes consolidating to a single log on each side is helpful, which we now know how to do that. So sometimes getting the same base in an exponential expression is what we need to solve things. It just depends on the type of problem that you encounter. So on these first ones, on the first one, we have log of x minus 6 equals 1. So as you're looking at this, what do you think you might try in order to solve this for x? Scorpion tail. What is my base here? 10. Very good. So a common base of 10 if it's not listed. And my scorpion tail looks like this. So I have 10 to the power 1 equals the location where I land, which is x minus 6. What's 10 to the 1? 10. And what will I do to solve 10 equals x minus 6? Plus 6. So x is equal to 16. As we solve these, especially with the log equations, we need to make sure that the answer we get at the end really works. We encountered that last time, a location where it didn't. We need to make sure that we actually put that 16 in for x. I don't end up with a negative base or a negative inside of a log. So if I put 16 in for x, am I good to go on this one? Yes, I still have a positive inside of that log. So x equals 16 is in fact my solution. How about number 2? Yeah, scorpion tail. This one looks just like the last one we did actually in section 4.3. Exactly. It has the base that's an x, much like that one did. And scorpion tail will allow us to bring that out of the base. So I have x to the 1/4 power equals 16. So you can deal with it as a 1/4, and that's fine. And if you think of it it's like that, it's much like the one I just did, where I'm raising it to the power that's the reciprocal. The reciprocal of 1/4 is 4. So that's fine. If you want to think about the 1/4 in terms of its radical expression, what would x to the 1/4 be in radical form? 4th root. And how would we get rid of the 4th root? We would do the exponent of 4, right? We would raise both sides to the exponent of 4. So the operation that we would do next is exactly the same, no matter which form it is that we continue from. We're going to take 16 to the power of 4. And what is 16 to the 4th? Not square root of 16, 16 to the power 4. Yeah, it's like it should be a big number. Say that again for me, David.
65,536.
It's a big one. Is that okay in the x location in this equation? Sure. Right? That base equation, the base part where x is located in the equation simply needs to be a positive number. This is. So we're good to go on that. What could you do if you wanted to check that your answer to number 2 were right? You could. Yeah, so you could actually go back clear to the very beginning here. And you could actually take a look at that change of base formula. Whoops. And you could take, I still did it, log of 16 divided by log of the base, which was our 65,536. And you could make sure that it really equals 1/4 or 0.25. So you could check it that way if you wished. Most of these will have some kind of a check step that's pretty easy to compute if you wanted to check them, especially for the ones that you can't see. Maybe they're odd in the back of the book or something. All right, so number 3 is different. It's not at all like the other two we just did. Number 3 is an example where I have multiple logs involved on the same side of the equation, right? Multiple logs. So when I have multiple logs involved, I want to actually be able to push them back into a single log expression. The stuff we learned in 4.3. So what can I do to merge these into a single log expression? Yeah, I would multiply their inputs. So I'd be multiplying a minus 2 over 5 times a plus 3 over 10. Now, while it's perfectly fine for you to multiply the 5 and 10, it's probably counterproductive to actually multiply the top out. So I would encourage us to leave that top at least in factored form. If you want to consolidate the bottom to be an exponent or a denominator of 50, that's okay. Why is what? Oh, because I just captured the wrong letter or number. Thank you. Better? Yeah, it is better. Thank you. Okay, so if we want to consolidate a little bit more, you could probably write this perfectly fine as a minus 2a plus 3 over 50 equals 0. At this point, aside from the fact that there's this awkward looking thing in the numerator, it actually looks a lot like problem 1. I have log of a base, I've got an interior, and it equals a number. Right? Log on one side, not on the other. So I'm back to using a scorpion tail. It's actually quite friendly, though. It's 2 to the 0 equals, and then I have a minus 2 times a plus 3, which it looks like we might actually have to multiply out here in a moment. Let's see. Over 50. What is 2 to the 0? It's 1. So I'm going to save myself, well, I'll just make this a little bit smaller. So it equals 1 on the left. Same thing on the right. And then if I want to solve this, I would want to multiply both sides by 50. Or you can think of it as cross-multiplying. Right? I'm trying to get the a's solved for, so I'll multiply by the 50. So I actually have 50 equals a minus 2 times a plus 3. And it's super, tempting to say, well, we'll just set a minus 2 equal to 50 and a plus 3 equal to 50 and solve. That property only works if we're set things equal to 0. So it doesn't work to do that here. That 50 is not 0. So we are at the point now where we recognize I do, in fact, have to multiply that out. So sometimes I might, and sometimes I might not. Here I do. So a minus 2 times a minus 3 would be a squared. I have negative 2a and positive 3a, so that's positive a. And then on the end, I have negative 6. Now what? Okay, subtract the 50. I need everything on the same side. So I have 0 equals a squared plus a minus 56. We can attempt to factor. We can use the quadratic formula. If you want to be really ambitious, you can complete the square. You can use the AC method, slide and divide, or trial and error if you want to try factoring. This one factors pretty nicely because of that coefficient in the front. It's an easy option at least to try with trial and error. So I'm going to do a and a. What are my signs? Different, right. So I have one positive and one negative. I need two numbers that multiply to 56, and their difference is 1. Positive 8, negative 7. Okay, everybody good so far? So you see how this all ties back into things that we've already learned so far this semester. It's going to keep doing that. And then I can, because each of it is equal to 0 over here, then I can set each piece equal to 0. So if a plus 8 is equal to 0, what is a? And if a minus 7 is equal to 0, what is a? 7. Okay, but we have to check that both of them really work, right? I do have two solutions. Just because I have two or one, it doesn't matter. I always have to do it, but I definitely need to check on this. If a is negative 8, is that an okay input? Remember, you have to look way back up here at the very beginning. Is it okay to have a equal to negative 8? No is the answer. Do you know why, Levi?
Because negative 8 minus 2 over 5 would give you a negative.
Right.
Not that.
So this is where we would start. If I put negative 8 in, all of that will end up being a negative number. It actually will be a negative number on the other one as well. If I put a negative 8 in here, it'll also be negative, so it fails twice. But if I have an interior of a log in the problem, which I do here, the interior has to be positive. That one doesn't work, right? So x equals, or a equals negative 8 is what we would have called an extraneous solution. It's not a solution at all. How about 7? Will 7 keep everything positive on those interiors? It does. So it's actually the correct solution. We could have more than one. This one just had the 1 because of that as well. So a equals 7 works. A equals negative 8 does not. Okay, so that's an involved problem, right? Involved a lot of the things that we've learned this semester. Let's try another one. What would we do first to solve this problem? Okay, we need to consolidate the logs, and we're going to use, going to use division. Yeah, so the subtraction here means that I'm going to consolidate the logs on this one with division. Over here, I had consolidation of logs with addition. Okay, so good noticing. So we're going to write log base 4. The input on the first one's x. The input on the second one is x plus 2. And it's going to equal 2. Then what? Scorpion tail. So circle the 4 and draw my arrow around. So this is 4 to the power 2 equals x over x plus 2. What is 4 squared? Besides a game children play. 16. X over x plus 2. Then what? Yep, cross multiply. Okay, so you can think of it as that, or you can just think of it as multiplying by x plus 2. Either way will work. So this is 16 times x plus 2 equals x. So 16x plus 32 equals x. Then what? Subtract x, So I have 15x plus 32 equals 0. Now what? Subtract 32. So 15x on the left equals negative 32 on the right. And divide by 15, right? So my x value, and it doesn't actually simplify either, is negative 32 over 15. As always, we want to see, does that work? And what do you guys notice? It doesn't, right? It's going to give me interiors, at least on the very first one, an interior that's going to be negative. If I try to put negative 32 over 15 into here, I get a negative number, right? That's not okay. So what that means is that I only had one possible solution and it didn't work. So what's my answer? No solution. You can either write it out in words, right? No solution. Or the no solution symbol is the 0 with a line through it like that. There is no solution to this particular problem, right? Log base 4 of x minus log base 4 of x plus 2 will never equal 2. How is number 5 different than the last two that we've had? Yeah, there's a log on each side, right? So what could we do to make it look like the ones that we just did? Yeah, subtract. We're going to subtract a log. We don't want to divide. We want to subtract. So we're going to move the logs so that they are on the same side. So we're going to subtract this one since it's got the 1 right here next to it that we don't want to shift to the other side. So minus log of x minus 1. So over here now I have log 4 minus log of x minus 1 equals 1. At that point, it looks a lot like the things we've already done. So what's my next step? Division. So this is a common log. It's just log. 4 on top, x minus 1 on bottom equals 1. Then what? Scorpion tail. My base is a 10. You guys told me that before. So this is 10 to the 1 equals 4 over x minus 1. 10 to the 1 is 10. And we'll multiply by x minus 1. So what's my next line look like? X minus 10 equals 4. Okay, is everybody good so far? Wonderful. Now what? Add my 10. So 10x equals 14. And then divide by 10. Those are both even, so it will reduce to 7 over 5. Okay, so that's my simplified expression. Or you can write it in decimal form. If you want to use decimals, this is 1.4. That's fine too. It doesn't matter. Am I allowed to use those values? Are they okay? Looking back at the original equation. Yeah, and the 1.4 actually makes it easier to see it maybe. But I definitely can put 1.4 or 7/5 into this, subtract my 1, and still have a positive number. So yes, I'm good to go. Either version of this would be a correct solution. Okay, last problem. Are you ready? What's my first step? Combine them using multiplication. All right, so I've got log base 3, and I'll have x times 1 over x equals 0. So what is x times 1 over x? It's not x. It's 1. Right? When you multiply a number by its reciprocal, x times 1 over x, you get 1. So this is log base 3 of 1 equals 0. If I were to rewrite this with a scorpion tail, because I didn't happen to notice it right away, what would I find out? 3 to the 0 equals 1. Is that true? Yeah. This is a true statement, right? So we had this situation come up, I can't remember when it was, but it was earlier with equations, maybe in chapter 2, where at the end of something, all of a sudden there's no more variables, right? The variable just disappeared somewhere. I mean, it did. It canceled itself out in this particular problem. But what I was left with is still a true statement. 3 to the 0 really is equal to 1. And that's true, right? Yeah. So what that means is that all values work as long as they're values that are in the domain. So what x values are we allowed to have in this problem as it was originally given to us, right, inside of the logs? What x values am I allowed to have? Got to have numbers greater than 0, right? So greater than 0 will work for both of these, yes? I mean, there are two separate things that we have to consider. We got to make sure that just a flat out greater than 0 is sufficient, it's enough. And it is. The x over here being greater than 0, that's true. 1 over x, as long as x is not equal to 0 and it's greater than 0, which it would be at the same time, is enough for it to be true. So down here, my solution is all x greater than 0. Now, what would have happened down here if this statement had not been true? right? Like, let's say I did the same problem, but instead of having what I have here, this is log base 3 of x, I had plus log base 3 of 2 over x equals 0. And as I consolidated them, log base 3 of x times 2 over x equals 0. I ended up with log base 3 of 2 equals 0. And I rewrote this problem, and it ended up saying 3 to the 0 equals 2. So this is actually a false statement, right? So one option is that the variable disappears and it's still a true statement. The other option is the variable disappears and it's false. So if the variable disappears and it's true, we get all the values that are actually valid that x could be. What happens if it's false? There's no solution. Okay? So anytime we ended up with equations where we were seeing this too, that's what happened. If the statement was true still at the end, it's all real numbers that work in the equation anyway. And then if the equation ends up not being true at the end, then there simply is no solution to that particular equation. Okay? All right, so 4.3 and 4.4 will be due on Tuesday. Okay, I will be collecting at least one of them. And then we will have a quiz on Tuesday of 4.2, 4.3, 4.4. And we'll be reviewing on Tuesday. So a lot going on Tuesday. Have a good weekend.